now Alex Lubotsky, who does not need any introduction, will speak on uniform stability of higher rank lattices, and his collaborator is around, so we can discuss things with him. Bharatram.
Okay, thank you. This is the first talk in a series of three. The other two will be given by Bharat Rangarajan, who is, I guess, with you now, even though I cannot see him. And this is a joint work of Lev Glebsky, Nicola Monod, and Bharat on uniform stability of high-rank lattices. So I'll try to give the general introduction, and the young generation who are better and smarter will give you the more deep and technical details. I want to stress, first of all, that this is a kind of rigidity. So let me explain. So let G be a semi-simple Lie group over a local field K. And for this audience, I don't have to explain what is a lattice in gamma, discrete subgroup of finite covolume. This can be uniform, co-compact, or non-uniform. We denote rank of G, the K rank of G, when the field we work in. Just for simplicity, we can talk also about mixed fields and, arithmetic, S-arithmetic, but all the ideas are already in the simple group case. Now we know we have a lot of experience with lattices, and we know that usually there is a difference between rank 1 and higher rank. Regard the questions like local rigidity, strong rigidity, super rigidity, congruence problem, etc. More or less at the division between SL2Z and SLNZ for n greater or equal to 3, but we remember that not always. For example, super rigidity is true for all higher rank, but also for some rank 1. Now, this talk is about Ulam stability or uniform stability. It's the same. Some people call it Ulam stability, some people call it uniform stability. Some people who don't want to get to the argument whether I should call it Ulam stability or uniform stability, just call it U stability as a compromise. And let me just say something which is clear to everybody here, but I just want to say it. What does it mean, usually rigidity? Usually rigidity means that there is a clear, easy to understand family of representations of the lattice gamma, and the rigidity theorem says that if something is also similar, it is already in the family. For example, if you take what is super rigidity, you have a lattice gamma. There are clear finite dimensional representation of gamma. Those who are coming from the Lie group, the algebraic representation, and the finite representation, those which factor to finite quotients. And the super rigidity theorem tells you that basically every representation of the group gamma is a kind of a combination of these two, tensor product or something like that. Ulam stability is such a statement for almost representation. So let's make it precise and more carefully. Let gamma be a group. Just now, any say finitely generated always for us, and G will be a family of Gn, which are groups, and Dn, which are bi-invariant matrix. Each Dn is a bi-invariant metric on the group Gn. We say that gamma is uniform or Ulam stable with respect to this family if for every epsilon greater than 0 there exists delta greater than 0, such that for every n and for every map from gamma to Gn. Now map here does not mean homomorphism. Map just mean a function. Assume you have a function from gamma to Gn, which is almost homomorphism in the following sense. Dn, the distance between phi of gh and phi g phi h is less than delta uniformly, namely for every g and h in gamma, the phi of the multiplication is almost the same. So this is an almost representation. Okay, how you can get such a representation, such an almost representation? There is a trivial way to get almost representation. Take an honest representation and deform deform it a little bit. But the stability means that the converse is true. Namely, if you have any almost homomorphism, then there exists an homomorphism psi, a true homomorphism from gamma to Gn, such that the distance between phi g and psi g is less than epsilon for every g and g in a uniform way. Namely, every almost representation is just a small deformation of a true representation. Let me put right away a big warning. Don't confuse it with the ordinary. There are two types of stability which can be studied for a given group gamma and the family, like before, of Gn and with Dn. There is the question of ordinary stability and uniform stability, and they are different, and the answers to the questions are different. Kind of a quick way to see the difference, or kind of to illustrate, let me explain what is ordinary stability, and let me redefine uniform stability. And it's a little exercise to see that the redefinition is equivalent to the previous one. We say that the group gamma is stable, ordinary stable, with respect to this G before, if for every family of maps from gamma to Gn, such that for every G and H in gamma, the distance between G and between phi n of GH to phi n G times phi n H goes to 0 when n goes to infinity. So this family of maps for every G and H looks eventually like a homomorphism. Then there exist true homomorphisms from gamma to Gn, such that the distance between phi n G to psi n G goes to 0 when n goes to infinity for every G in gamma. But in this case, the assumption is local. For every G and H, it goes to 0 with some rate. And the distance which we require is also with some rate. Uniform stability means that we have, again, such maps, such functions from gamma to Gn, but the supremum over Gh of gamma, or of all G and H, between phi and Gh and phi and G, phi and H goes to 0, which means we assume a much stronger condition. We assume that that it's almost homomorphism in a uniform way on G and H, but in this case, we expect a stronger conclusion. We expect that there exists psi n from gamma to Gn, such that the supremum of G between psi n of G, between phi n of G and psi n of G goes to 0. Namely, we assume uniform almost, and we ask for a uniform deformation, like very close to a true homomorphism. So this is just a warning, because these two types of questions are studied in the literature, and they are not equivalent. I want to stress this. But sometimes you can learn from technique in one to the other. I will illustrate this soon. Okay, today we will talk only on one case. There are other cases to study this type. There is cases of even with finite group, the symmetric groups, and there are actually, I just give an hint, some questions of this type which are important in computer science, but I will not elaborate at all on this today. Today we'll talk only on the case where Gn is Un, the unitary group, and Dn is some metric induced by submultiplicative norm on M and C. For every norm on N and on M and C, we can, which is submultiplicative, means well, we can define the metric without a submultiplicity, but we will work only with submultiplicative norm, namely the norm of AB is at most the norm of A, the norm of B. We can define the metric Dn between A and B simply the norm of A minus B. Examples: the operator norm, what is called sometimes the Frobenius norm, which is simply the L2 norm, or in more general, the P-Schachte norm for every P between 1 and infinity, which is the norm, if you take a matrix and you take A, not A times A, this is A joint times A, then the A adjoint times A is always a non-negative definite, namely it's normal operator, the eigenvalues are non-negative, so we can take square root of it. This is the absolute value of A. We take the absolute value of A to the P, we take the trace of it, and then 1 over P. This is called the P-Schachte norm. I want to stress that there are uncountably many norms here. For each one of them, it's a different problem. You cannot, at least we don't know, to deduce, assume you know that a theorem of stability of group with respect to one norm, it's completely different story with respect to another norm. Even if the norm, you not say that one norm is always bigger than the other. If norm A is bigger than norm B, which means that the assumption you make here, you see, let's go back to the previous slide. If one norm is bigger than the other, so if this satisfies with respect to the bigger norm, it certainly satisfies with respect to the smaller norm, which means a challenge for the bigger norm is certainly a challenge for the smaller norm. But assume you can solve it for the bigger norm, that this goes, sorry, I said it incorrectly. Assume this goes to 0 for the smaller norm, you don't know that it goes to 0 with the bigger norm. And if you can solve it for the bigger norm, you don't know if you can solve it for the smaller norm. Now I'm confused. If you solve it, for the smaller norm, you cannot know that you solve it for the bigger norm. Anyway, think about it. I got confused, but it's if you think about it for a second, you see that you cannot deduce from one to another. For example, if we take the Hilbert-Schmidt norm, which is by definition simply 1 over square root n of the standard L2 norm, we cannot, if a group is stable with respect to Frobenius norm, we cannot deduce that it's stable with respect to the Hilbert-Schmidt or the opposite. We really cannot. And now we're going to solve the problem for Frobenius, and it's still open for the Hilbert-Schmidt. For a reason that will be later clear, this little property of submultiplicative, which is true for Frobenius and not true for the Hilbert-Schmidt, this condition is essential for us. It's frustrating, but this is what we have. Okay, so the main theorem, as I said, is a joint work with Lev Glebsky and Nicola Monod and Bharat Rangarajan. Is the following. Let G be UN Dn. Dn any submultiplicative, namely Dn coming from a submultiplicative norm. Let gamma be a lattice in G. G is the I-rank simple Lie group over some local field. Then gamma is Ulam stable, provided G, the group G, not gamma, satisfy some condition GQ1, Q2. I will explain what is GQ1, Q2 only later. I say now that this condition is known to be true for most simple groups, but unfortunately not to all. In fact, it's not true for some. And unfortunately, our theorem is very, very general. It covers, in some sense, almost all groups, but not all groups. There is an interesting challenge here to make it a complete results. And you see, this is a kind of rigidity results, right? We are saying that every almost representation is near a representation, so it's kind of a super rigidity for almost representation. Then, and if it's representation, then Margulis' theorem tells us exactly what we are. So you can put it in line that if Margulis' super rigidity tell you every representation is something that we well understand, this theorem tells you that every almost representation is something that we understand very well. But we need here this assumption. The GQ1, Q2, it's satisfied by most simple groups. For example, it always satisfies if the field K is non-Archimedean. It always satisfies when it's actually always satisfied for complexly groups, but for SLDR I wrote SLDC, but it's actually satisfied for all the complexly groups, and it's always it's satisfied for SLDR if D greater or equal 4, but not for D equal 3 for some reason that we'll see later. Okay. What is the history of the subject? The first theorem of this kind is due to Kashdan already in 1982. He proved that amenable groups are strongly Ulam stable with respect to the operator norm. Strongly means, you see, we define Ulam stable that every almost representation to UN can be is nearby a true representation. He proved that this is true for amenable groups, even for the unitary group of infinite dimensional Hilbert spaces, not just to finite dimensional one. That's completely general results. But Burger, Rojava, and Tom in 2013 said it's impossible for lattices to have the strong Ulam stable, because they proved that if gamma is any discrete group containing a free non-abelian group, then gamma is not strongly Ulam stable. Why? The proof is not complicated. It was known before, which is a nice result. It's not difficult, but it's not completely trivial. There is a nice idea. I will not stop for that. That free groups are not Ulam stable. By the way, it's trivial to see that free groups are stable in the ordinary sense. And so you see that to be stable in the ordinary sense and to be stable in the uniform sense, it's not equivalent. Anyway, free groups are not Ulam stable. So what Burger, Rojava, and Tom did, they said, okay, for free group, we have finite dimensional almost representation, which are not nearby representations. So they induce them up from the free group to gamma. The free group is of infinite index, so you get an infinite dimensional representation, and show it's something, those who know the proof of Kashdan property T, how you go from a group to a lattice and vice versa. They show that something like that is true for almost representation. So you show that the group gamma, now when you reduce for the free group, also has almost representations which are not nearby representations. By the way, it used to be a famous open problem with whether every non-amenable group contains a free group. Now we know that this is not the case. There are non-amenable groups which without free subgroups. So this leaves the comparison of this theorem, leaves the open problem. Maybe strong Ulam stability does characterize amenability. We don't know about groups which are in between, namely they are non-amenable but without free groups. What is the answer in these cases? But let me continue with our main that Burger and Rojava also made a connection between this subject and bounded cohomology. This is not a difficult result, but I don't want to that. Maybe Bharat will elaborate on that. If we know that always there is a canonical map between the bounded cohomology of gamma with coefficients in R and the ordinary cohomology, and they prove that if this map is not injective, then gamma does not have Ulam stability. Some of you know that this is not injective if and only if there are many quasimorphisms to a non-trivial quasimorphism to R, and then you can take exponential of them, and then you get almost homomorphisms to S1. You can imagine what is the proof of this, which is not so difficult. As a corollary, which maybe, I'm not sure, maybe was not known at that time, various people proved some cases, but I think it was Koji-Fujiwara who proved the general case that if you take a lattice in rank 1 group, then this map from the bounded cohomology to the ordinary cohomology is never injective. So lattices in rank 1 groups are not Ulam stable, never Ulam stable. Okay, not even with finite dimensional. In fact, not even with one-dimensional representations. Now, Burger, on the same paper in the Israel Journal, Burger, Rojava, and Tom gave the first hint that maybe the situation for lattices in I rank is different. They showed that SLDZ, and in fact even more generally SLDOS, where O is the ring of integers in some number field localized at S, that all these groups are Ulam stable when D is greater or equal to 3. Their proof uses in an essential way, and once you know bounded generation is not that difficult, they use that the bounded generation of this group, they prove it as a corollary to the bounded generation. It needs a proof after that, but they use that. At that time, when they prove it, well, the situation as of now is that some of the non-uniform lattices in I rank simple Lie groups are known to have a bounded generation. I understand that in the continuation of this conference, there will be some talks about that by Ren and others, maybe. And then bounded generation for non-uniform, and maybe one can believe that and it's still believed that all of them have bounded generation. So maybe one day it will be possible to prove the Ulam stability via this method for non-uniform lattices. But quite recently, like 2-3 years ago, Korvaja, Rapinchuk, Gren, and Zanier made a big breakthrough when they surprised all of us, at least me, showing that co-compact lattices are never boundedly generated, never bounded generated. So the method of Burger, Rojava, and Tom cannot be extended to work for a general I rank lattices. Let me anyway mention that there was a feeling of connection between Ulam stability and bounded cohomology, not bounded generation. These are not the same thing. And they're not equivalent, or as far as I know, I don't think that anybody know to make a kind of connection between them, except of the fact that the word bounded appears in both. What looks like an int. We talked before, sorry, not yesterday, I mean in the previous slide, that if gamma is amenable, then it's stable, and H bounded, the bounded cohomology of amenable group are always zero for every n. Similarly, or almost similarly, if gamma is a high rank lattice with no fixed point, this is going to make some problems to us later, then the bounded generation N, H, and B, gamma V is zero. Now, this is a big difference than rank 1. You remember in rank 1, we mentioned that H2 of a rank 1 lattice is never trivial. In fact, it's even infinitely generated. It's of infinite dimension, sorry. Now, this theorem was proved first for n equal 2 by Burger and Monod, then a different proof by Burger and Yehuda Shalom, and now I mentioned this because this is going to, the proof of this paper going to be important for us. Oh, it's not Burger Shalom, it's Monod Shalom, sorry. The second proof is by Monod and Shalom, not by Burger. The first is Burger Monod, the second is Monod Shalom, and the third is Monod for all n. I'm sorry. The second Burger should be Monod. Well, Monod was a student of Burger, but still this is the work of Monod. Okay, now all these ints are kind of, and you know, the theorem of Burger that SL and Z for n greater or equal 3 and Ulam stability led Monod in his ICM talk in 2000 to ask, is there a connection between Ulam stability and bounded cohomology? It didn't make any precise conjecture in any direction, just say that's in a connection. And now we understand that the answer is yes, but. And this but causes a lot of trouble, as I will explain in a minute. But before we go to that, let me take you back a few years ago to another work, a previous work which I did with the Schifre, Glebsky, and Andrei Storm, which was about the ordinary stability, not the uniform stability. Okay, unfortunately, we will have to use here the language of ultra product and ultra limits and this model theory. It's only, in some sense, only language, but you'll see it's more convenient in this situation, and I will explain in a minute why. Let U be a ultra filter of the natural number. Now, we are talking about this group, unitary group UN. Let Ln be the Lie algebra of them. And take the norm, you know, we are working with some Dn matrix, we're coming with norms. I put also the same norm on the Lie algebra, right? The Lie algebra is a sub-Lie algebra of the n by n matrices. I take that norm. And now I'm taking the ultra product, the topological ultra product of Ln, I call it L. Those who are maybe not so comfortable with the language of ultra product, just think about it. You take the direct product and essentially you divide it by all the sequences which converge to zero. So this is the topological ultra product of Ln. Now, why this is convenient for us? Because you see, we have almost homomorphism phi n to un, right? Un acts on the Lie algebra as homomorphism, right? The joint representation. So basically, we can think of it as almost representation acting on this Lie algebra, but as almost representation. But if you think about it, if you had such a sequence of almost representations, which are kind of better and better, the distance, the action is getting, they look more and more like homomorphism. If we divided L by all the sequences which going to zero, then this infinite sequence of maps phi n, which are almost homomorphism, define a true action of gamma on this ultra product. It's not anymore almost homomorphism. It's one homomorphism on this infinite dimensional Lie algebra, on this ultra product of Lie algebra. So now we are back. Why this is so convenient? I want to stress this. This will come up in the lectures of Bharat, and this is one of the source of the difficulties in our work. And that now we are working this ultra product, but the benefit of this, that we are not anymore in the world of almost, which is very difficult. Take almost homomorphism. What is the kernel of almost homomorphism? What is the image of almost homomorphism? You can always move it a little bit, right? And now the main technical theorem in the previous work of the Schifrin, Aleksy, Tom, and mine was that if H2 of gamma with coefficients in this crazy L is zero, then the sequence is close to true homomorphism in the sense of ordinary stability. Okay, and then we prove it for some lattices. We use Garland theory about vanishing cohomology, etc., to show that many lattices have this property, and recently with some work with Uri Bader and Sauer and Shmuel Weinberger, we showed it for many lattices in the more or less. Now we have a kind of a stability with respect to ordinary stability for high rank lattices, at least for most of them. But I don't want to elaborate on that. I just wanted to take this as suggestion. Why? Well, yeah, maybe before suggesting, usually when I gave talks on that in the past, people were surprised how H2 is coming to the game of this stability. Why H2 is so important? So let me just explain this. This is easy to explain. You see, you remember we started with phi n from gamma to un, which are almost homomorphisms. Now, these maps from gamma to un give you a diagonal map from gamma to the product over un. But on the product is not homomorphism. If you divide the product by the what we call infinitesimal, those elements which converge to zero along the ultra filter, but forget about it if you are not comfortable. Just think about it. If you kind of identify sequences which are very close to each other, getting the distance go to zero, suddenly now phi star from gamma to this is a true homomorphism. And the map from product of un to the product of un mod inf is a true homomorphism. So this is homomorphism. And here is a little exercise to think about for a second. That stability is completely equivalent to the existence of extension psi, which will be homomorphism. You see, to start with, we have the diagonal map from gamma to the product as not homomorphism, just almost a sequence of almost homomorphism. If we have an homomorphism from psi to this product, which close the diagram, then what it really means? It means that we have infinitely many homomorphisms to the product, which are close to phi star because modulo the infinitesimal, they equal to the phi ends. So that's completely equivalent. And now I'm talking the ordinary stability. You'll see there is some delicate point when we come to the uniform stability. So suddenly you see that the question of stability becomes a question of lifting homomorphism from one group to a bigger group. And this is something that, mathematicians have studied for many years and developed many methods to do it. So, but what's the problem here? The problem that mathematics knows to handle this question using H2, using cohomology, if the kernel here between this product to disks is a billion. For a billion kernels, we know that's really vanishing of H2. But for another billion kernel, in principle, you can say that it's vanishing of H2, but it's a vanishing of H2 with coefficients in a nanobillion non-commutative module. It's sort of even difficult to understand or to define what exactly it is. So the problem is that in general, it's very difficult to handle such a lifting problem if the kernel is non-commutative. And here, the kernel from this group downstairs is extremely non-commutative. This kind of all the infinitesimal, all the sequences in UN which converge to zero, to the identity, sorry, it's not even a closed subgroup. It's something very crazy. But the key step, kind of the key new idea in some sense, if you want, is that if the norm is some multiplicative, that's why we need it, we can approximate this K by a billion quotients, one after the other. I don't have time to explain it. Bharat will go over it, but it's just like in the congruent subgroups. Take a map from SL3Z to SL3P. The kernel is very non-commutative, the congruent subgroup mod P. But the congruent subgroup mod P modulo the congruent subgroup mod P square is a billion. P square modulo P cube is a billion, etc., etc. So there is a situation like that here, and if we know vanishing of cohomology, we can extend this psi in small steps and then take the limit to get this. So this was the method in the previous paper. Now our work with Bharat and Aleksy and Monod started to try to apply the same strategy, which in principle can work with uniform stability. But very quickly, if you start to do it, you see that the relevant cohomology here, again, hopefully Bharat will have time to show it in more details, that the relevant cohomology is the bounded cohomology instead of the ordinary cohomology. But there is, at the beginning, I have to admit that we thought, okay, we have bounded cohomology, fantastic. We have all the results ready about vanishing of bounded cohomology. Oh, we can plug in the known results. We will apply the same machinery, and we'll get a nice results for the Ulam stability for high rank lattices using bounded cohomology, like Monod expected. But when we start to write it down, we realize the issue is much more delicate. And it's very delicate, became so complicated. I have to say that Bharat actually joined us a little bit later after we kind of had the beginning, but it became so complicated. It's only due to Bharat that we could finish this. The paper is eventually 80 pages. Why? Because we have to develop a new type of cohomology. But Bharat will explain you that cohomology in details. I'll just give you a few hints. The problem is that you must speak the language of non-standard analysis, and to understand that we need not just a lifting psi which is some lift, we need it to be internal in the language of non-standard analysis. In the ordinary stability, we didn't come to this problem because we really care about the value only of the generators, and then everything is internal. I don't have time to explain it. It will come again, I'm sure, in Bharat. I see that my time is almost over, so we need the following. What we really need here, that if the group, like if we imitate the previous work to this context, then we can say that gamma is Ulam G stable if and only if every homomorphism phi that has an internal lift as a function, not as a homomorphism, also has internal lift homomorphism. And then we can do that. But to catch this internal, we have to develop a different language and develop a new cohomology theory, which we call it asymptotic cohomology, and we denote it HNA instead of B of gamma with coefficients in that Lie algebra, which is the ultra product of these Lie algebras of UN. And what we really need is that's what we prove, that if the asymptotic cohomology vanish, blah, 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 then the phi n are near true homomorphism UN in the uniform stability sense. Just a few more minutes, so let me just say that just like there is the canonical map mentioned before between the bounded cohomology to the ordinary cohomology, there is a canonical map from the asymptotic cohomology to the bounded cohomology, but we have no idea if it is injective, surjective. This is kind of a brand new type of new cohomology. I hope people will be interested and maybe can answer such question. For example, if we would know that this injective, our life will be much easier, and the full theorem about high-rank lattices would be proved. It's just that we don't know that this is injective. I wish we would know. Maybe it can be proved. Maybe we are missing something. Anyway, what we can do, we can show that the asymptotic cohomology of amenable group vanish. So this kind of, we can recover Touchdown theorem, but I have to admit that it's not really new. It's the same type of proof as before, but in our language. Okay, I see that I have 1 minute, but because I started 1.5, 2 minutes late, I will allow me. Maybe I just say something. Okay. The strategy of the proof, what we really want to prove is the vanishing of this new cohomology for high-rank lattices, H2, just only H2. We follow the basic methodology of Monod Shalom to prove the vanishing of H2 of the bounded cohomology for high-rank lattices. But every step has a lot of difficulties. Shapiro lemma, which is such a standard, almost trivial lemma for lattices, it become a complicated issue here. By the way, even Shapiro lemma for non-uniform lattices is not so trivial. I should refer you. There is kind of a breakthrough of Bader and Roman Sauer recently, a few weeks ago. They put on the archive an amazing paper which they kind of resolved this issue, something which people in automorphic forms kind of bother around this. Borel and others for many years, they used geometric group theory they actually created a new type of cohomology, something in the same spirit of something they call polynomial growth cohomology for non-uniform lattices, and show that using this cohomology, you can overcome many difficulties which happen there. Anyway, I just want to mention that, eventually what we really have to do is kind of induction from the ultra product from the ultra power of gamma to the ultra power of G. The ultra power of G is not any more locally compact group. There is no really R measure. So what does it mean L2 of G star over gamma star? So everything you have to define again and to do it and to work it out. And well, luckily we had Bharat with us. And I'm skipping this. I want to go because I cannot leave you without defining this strange condition GQ1, Q2. So you will see how things are delicate here. You remember I said the theorem was that we have stable, Ulam stable, uniform stable for all lattices in simple Lie group, provided G satisfy this strange condition. What is this condition? The condition is that G has two parabolic subgroups, Q1 and Q2, satisfying that the intersection contains the minimal parabolic P. That's not difficult to satisfy, and Q1, Q2 together generate G. So it cannot be the full G because the it's a proper parabolic subgroup, of course, such that H2 bounded, yes, we need some assumption on the bounded cohomology of Q1, of Qi, but for both of them, with coefficient is R to be 0, and we need H2. Now, you remember I told you that H2 vanish. Well, I told you that H2 vanish if there is no trivial submodule. But if there is a trivial submodule, it's not necessarily vanish. And for example, take SL3. If you take SL3 and you take a proper parabolic subgroup, then Q is an extension of a minimal group by SL2R. For SL2R, it's a rank 1, it doesn't vanish. So sometimes this is not satisfying. And sometimes we don't know if it's satisfying. Anyway, and we need also the H3 vanish, or at least will be Hausdorff. If we have this condition, as I said, this happens for most groups, but unfortunately not to all groups. So our theorem is fairly general, but not yet complete, not yet covers all the high rank lattices. But we strongly believe that it's true for all high rank lattices, and somebody can come up and find a shortcut or another way to finish the proof. Okay, that's all.
Alex.
Thank you very much.
Any questions?
Hello. What do we know about Ulam stability of general property T groups?
Just by definition of property T, nothing lattices, etc. We basically know nothing.
Only
In
for
fact, what?
Only we know for lattices.
We only know for lattices. The proof goes very much via lattices. You see, we start with the group. We take the induction. We induce we imitate the proof. What it's known in the bounded cohomology, that you can take the standard Shapiro lemma, you can induce a presentation, and they are equal. But as I said, even this little lemma is very complicated for us. But once we have this lemma, the next results are always about the group G and not about gamma at all. We forget about gamma after the Shapiro lemma, and we only work with G. And therefore, in those cases where we succeeded, we had the results for all the lattices of gamma, because we really didn't work with gamma after the Shapiro lemma. After the Shapiro lemma, we work only with G and not with gammas.
Okay.
So I know nothing about other groups with property T. Here is an example which I know nothing about: random groups. Random groups in the density between 1/3 to hold on. Hold on, they are parabolic. Oh, they probably don't have. Hold on. Koji, where is Koji? I don't remember now if the results of Koji for Girava was for every hyperbolic group. Okay. Yeah, maybe we can say something. I think that the results of Koji for Girava was, I'm not completely sure, that every hyperbolic group has infinite dimensional bounded cohomology. This by the results of Burger, Tom, and Ojava means that they are not uniform stable.
Okay, so
Yeah, that's interesting. Which means that usually, if I remember correctly, that he didn't prove it only for lattices, prove it for every hyperbolic group, because you see the random groups between 1/3 and half are T and hyperbolic. So that means that our results are very spatial for lattices and are not true for general Lie groups. But I should check it. It's just that it's skip. I'm old guy with little dimension. So I don't remember now. I will check it.
thanks.
Hello, Alex. This is Gopal. So you started with the group UN, which is, of course, compact over.
I cannot hear you. Gopal, are you talking to me?
Yeah, I'm saying that your example in the beginning was the group UN.
Right.
Unitary
Unitary
group.
groups, yes.
So it means that you were working over non-Archimedean fields, because otherwise the group is compact.
No. I work, the maps are always to UN. The gamma can come from a non-Archimedean simple Lie group.
And the
This is a theory for UN. Now you can develop, you see, the area of stability is only in its infantery, it's only starting in the last couple of years. Suddenly there is hopefully a lot of interest. I should mention the young guy, Francesco Fournier, who developed the theory when the family of groups that you map into are compact p-adic Lie group with the ultrametric norm there. It's a different theory. They are not the same. So it's really, this theory is a kind of depends on gamma. It depends on the family GN. It depends on the DN. There is still a lot of work to do for a generation of mathematicians to solve all this problem. What is beautiful that each case brings interesting connection, with model theory, with cohomology. There is actually very interesting connection with computer science if instead of UN, you take the symmetric group with the Hamming distance. In fact, even UN has a connection with quantum computation. The big breakthrough in the recent year about this results in quantum computation, which is a corollary solve the constant embedding problem, uses stability of into UN with respect to the Hilbert-Schmidt method. But what they study a family of finite groups maps into UN, and you want something which will be uniform in the family UN and in the family of finite groups. Every finite group is stable in our sense by itself. But if you want it to be with the same epsilon and delta, then it's much more difficult. But it comes even in quantum information theory. And if you do CM, it comes in a different way. It's became a very wonderful subject with connections in many directions.
Thank you. Any more questions?
Hi, Alex. Venki here. Hello.
Hi, Venki. Yeah, welcome to Bangalore. I wanted very much to visit you there. I found another opportunity. Sorry, I'm not coming. Yeah.
But when you're looking at homomorphisms of gamma into UN, unitary group, for higher rank lattices, there are very few, right? They will have finite images most of the time.
Okay, right. So basically, yeah, basically what we are saying, you are right, that if you take an high rank non-uniform in the right, there are very few, so this theorem is indeed very strong. It tells you that the almost representation are just little representation, little deformations of this. Yeah, thank you. I really had to stress this, that it's a kind of a very strong theorem in the case of, especially for non-uniform, because there are so few and we understand them all. We can even count them in somehow.
Thank you.
Thank you. Any more questions?
Can I ask a question? So you said that the SL3R does not satisfy the condition GQ1, Q2. Is there any
Right.
other example of a simple real Lie group which does not satisfy GQ1, Q2?
Yeah. They take the symplectic group.
Mm-hmm.
In the symplectic group, the problem is that you take a parabolic group such that the quotient is a smaller symplectic group. Then the smaller symplectic group has the non-trivial H2 ordinary because it's a central extension. But it's known that it's even a bounded central extension, namely the H2 of P is not trivial. And so the condition is not satisfied.
So,
I don't think you have to give up on that, because I think maybe there are some ways to avoid it, but we couldn't find a way to.
you mean in the case of the SP2 and R for any n, your condition does not hold?
Right. Now I haven't looked at our paper for quite a while, but it's, we know when this is known, the H2 and H3 condition. When I say we, I mean especially Nicolas Monod, who is the world expert on bounded cohomology. In fact, some people are working and improving the situation with H3. You remember I said that we need also H3. We need also H3 to vanish or to be out, though the situation seems to be improving. Our paper gave further motivation to people in bounded cohomology who study this problem anyway. They were interested in that for their own reason. Now I don't remember what the state of the art, at least our paper, we described the state of the art of a few months ago, but maybe even now there are little improvements on this H3. But there we more or less classify among all the simple group of real type when we can prove it and when we cannot prove it. I want to stress, for complex groups, or if K is a non-Archimedean group, it's always satisfied. So our results is complete. But for real simple group, it's not complete.
Thank you very much.
We thank Alex and we stop here.
Thank you very much. I hope to be with you at some point in the not too far future. Thank you very much.
Thank you.